Title of Chapter 5, Boundary Problems.
Orbit determination from two positions of time.
Okay. So basically this is what we call the Gauss problems. And sometimes the people call this Lambert problem. Lambert is a name, and Gauss is also a name. And Lambert basically is a pioneer of the problem and before Gauss, but the people kind of mix using the two problems. And the problem statement of this is that given, so you will see a little bit different from our previous calculus problems. So here, this is the given two positions, R1 and R2. So we know the two positions, and we're going to calculate the corresponding velocity V1 and velocity V2 at the two positions. So which means, assuming, let me draw the orbit. So if this is orbit, and say this is our focus. Okay, so basically here we are given is R1, and here we are given is R2. Okay, and we want to determine the corresponding velocities here. Basically, this is a prediction problem. So how we what kind of applications for this kind of problem statement? Here I can address a little bit. So for example, here is, say, this is the launching site on a certain place on the Earth's surface. Okay. And for example, this is the certain point in space. You're going to intercept with something, for example, common missiles, or you're going to rendezvous with international space stations in the space orbit. So in this way, you know the R1, that is the locations of the launching site. You know the R2 in advance because you know that space station is going to pass through that point at a certain time. So you have pre-knowledge about this one. So you can calculate the V1 and V2. So basically V1 is the required launching velocity, and to bring that the spacecraft to here, and V2 is the velocity at the meeting at the connection. So that means you need to know this V2, and then you need to modulate basically V2 if you need to do kind of the velocity change to right away exactly to meet the things there. Okay. For the missile interceptions technologies, and basically that's based upon this. Okay, they using radars. They can they can calculate the R2. For example, this is the Oklahoma Greeley here, and they can use radar. They can track. For example, this is a missile coming to here along this certain track. They can predict their positions at any moment. So they decide this is the point I want to strike. I want to strike the common missiles. So they do the very quick calculation, determine R1, R2, then they come up with V1, V2, then they can rendezvous these ones. And in these chapters, we're going to have this kind of similar examples to exercise, and we see how can we proceed this one. Okay. So basically, for this, right now in the general problem statement, again, we are given R1, R2, and we don't know R1. We don't know what kind of the orbit will constitute for R1 and R2. That's the first question. Then the second question is this: is there or the unique orbit existing to constitute R1 and R2? We don't know yet. So for this question, usually it's more challenging than calculus problems. the calculus problems is difficult in a way, in a numerical way. Okay, we have to given the data t, then we have to come up with the corresponding anomaly angles, and so that one numerically is a little bit more rigorous. But in terms of the mathematics, it seems okay. For this kind of questions, basically here we have to determine the orbits first. Okay, so here let me give you certain terminologies. So for first one, we are given the R1. Let me draw here. So for example, R1, R2 is schematically drawn like this. Okay, and this is a point, and this is a point pointed by R1 and R2 respectively. The 2 points must be in the same orbit. Okay, and what kind of the orbit can constitute this? And there's 2 possibilities, and let me give to you. And one is this: assuming we have the orbit, say, how do you do that one? I try to schematically draw this one. Okay, so here this is the focus. So one way is the R1 going to R2. Go that directions. Okay, so which means movement of the spacecraft from this position to that position is in that directions. And the other possibility is this. So this is another possible orbit. And for this orbit, the connection, the movement from R1 to R2 is here. Okay, and that is the study result. Basically, there's 2 possibilities and 2 regions between R1 and R2. So from here you can see basically for the green one, that is usually we call this is, we give the terminology, this is called the short wave. Short wave transportations. And for this one, we call the long wave transportations. Okay, and the why we call the short wave. Short wave basically is the anomaly span is less than the 180 degrees, and for the long wave, the anomaly is more than 180 degrees, and that's the definitions. And depends on the which way, long wave or short wave you pick in the program later we're going to determine it, and that will change the velocity we're going to find. Okay, so that is the first thing here. And on the other side, if our initial positions R1 and R2 are collinear, like this case, or this case, this is called a collinear. Case. Basically, for this case, we don't have any solutions. Okay, numerically, this situation is infeasible. So that means we have to go to the special case considerations here. Okay. So now for these chapters, we only consider is the regular situations like this. R1 and R2, they span the two-dimensional. They are not collinear, and we only consider it this. So, Doc, you can go to the next